We've all heard it said that life is like a game. Most games, whether we work in teams or work alone, have well-defined rules with clear benefits for winning and costs for losing. And that makes them something we can think about logically and mathematically. But what about life? Can mathematics tell us anything about the competitions and collaborations that happen every day between individuals, groups, nations, even between animals or microbes? From the social sciences to biology, robotics, and beyond, the answer is yes. Welcome to Game Theory.
After all, we didn't do it. Just let us go. I got $5. I'll give it to you.
I don't want to hear it. You know the way.
Why not?
Come on.
Ow.
Get on the door.
But we didn't do it.
So, Mr. Blue, we got you dead to rights. Picked you and Mr. White up not a half block from the scene of the robbery.
We were out buying groceries.
We were out buying groceries.
Is that where you got this little item?
That doesn't prove a thing.
Doesn't prove anything.
Really? Now, what do you think your friend Blue will say about that?
He won't talk, he better not.
Look, I'm gonna lay it out for you. You talk, we let you go.
No jail time?
Not a zip.
What happens to White?
What happens to Blue?
He gets 90 days.
What if he talks and I don't?
Well, then he walks and you get 90 days.
What if he rats on me and I rat him?
Then you both get 60 days.
What if neither one of us talks?
Well, then it's a light sentence. You both do 30 days. But you need to ask yourself, how much do you trust your buddy?
Okay, he did it.
Now that wasn't such a good strategy, or was it? Both Mr. Blue and Mr. White end up in jail, but with the right combination, one or the other could have been free. Then again, if they had cooperated with each other and kept quiet, they'd still go to jail, but with an easier sentence. So what's their best strategy? Or is there one? Our two criminals are in fact caught in what's called the prisoner's dilemma, a classic scenario of modern game theory, which came into its own as a part of mathematics in the 20th century. You see, the point is that interactions are strategic, say cooperative or competitive, and how well we do in any given strategy almost always depends on the actions of others. The value of an interaction can be expressed in terms of a cost and a benefit, as in the loss or capture of a piece in a chess game. The great surprise of game theory is that it not only applies to games, but interactions in the real world, like the dilemma facing Mr. Blue and Mr. White. To do that, let's take a look at the game these kids are playing.
3. Even. 1, 2, 3.
It's called Odd Even, sort of a simple version of rock, paper, scissors. One kid takes odd and the other takes even. For each round, the kids choose to reveal either one finger or two. When they add up the number of fingers, if that number's odd, the kid who chose odd wins all the points. If it turns up even, the kid who chose even gets all the points. In every round, one kid wins and one kid loses. Pretty simple, and it doesn't seem like there's much strategy going on, but let's look further. The best way to understand what the odd-even game looks like in terms of who wins and who loses is to build a grid and look at how each single round or game could go. Let's put odd on the left and even on top. So if the first, odd, chooses 1 and even chooses 1, even gets the 2 points. And we can say, theoretically, that odd loses 2 points. We write it like this, starting with odd score being -2 and even score being 2, even's payoff. The second time, maybe odd chooses 1 again and even chooses 2. Now we've got 3, an odd number. So odd gets the points. Odd's payoff is 3, even's cost is -3. Third time, odd chooses 2, even chooses 1. Odd wins again, and again, odd's payoff is 3, even's cost is -3. Fourth time, they choose 2 and 2, and so on. Even wins. Now, if we're trying to decide on a best strategy, we actually have to do a little algebra and figure out the probability of each solution turning up. Now, here's where we see the magic of math. It turns out that if odd plays 1 7/12 of the time, odd will actually accumulate more points over time, winning the game. This is an example of a mixed strategy because odd has to mix up what he does. In fact, if you do only one thing all the time, your odds of winning aren't going to increase.
1, 2, 3, odd.
Just the opposite in the long run, because your opponent's going to figure out pretty quickly what you're doing. This kind of payoff matrix does help us see that our instinct for not making the same choice all the time is also a mathematically sound one. Odd even is an example of what we call a zero-sum game. I win, you lose. A player benefits only at the expense of others. If you add the payoff and benefit for each hand, they add up to 0. But most games are non-zero sum. A gain by one player doesn't necessarily mean a loss by another player, as in Blue and White's prisoner dilemma. Let's take a look at their payoff matrix to see if there's a best strategy for their non-zero sum game. C stands for cooperate, the choice to keep quiet. D stands for defect, the choice to rat the other person out. It's pretty obvious that mutual defecting gets the biggest jail time and cooperating gets the lightest, at least when we're talking about both people. But if we're looking for the best strategy for one individual, what we're really looking for are ways to maximize that person's benefits while minimizing their maximum cost. For example, let's pick Mr. Blue. If he cooperates with White, he gets a reward of a light sentence.
I don't know anything.
30 days.
But if Blue succumbs to the temptation to defect and White cooperates, Blue goes free and White gets the worst punishment, the sucker's payoff.
White did it.
90 days for White. Blue is free to go.
And if both Blue and White defect, it's the harshest punishment for both of them.
White did it.
60 days, the both of you.
So what's a prisoner to do? If I'm a prisoner, the potential payoffs really define the game. They're ranked in this order. T, temptation to defect, is greater than R, the reward, which is greater than P, the punishment, which is greater than S, the sucker's payoff. And if we plug in values, the payoff matrix clearly shows the stakes and the dilemma. Because it seems like choosing to defect is always the best strategy. In mathematical terms, P is what we call the minimax solution, a choice that minimizes the maximum loss. Hungarian-American mathematician John von Neumann described the minimax solution in 1928 and effectively established the field of game theory. Using functional calculus and topology and chess, von Neumann proved it possible to work out the best strategy in zero-sum games that would maximize potential gains or minimize potential losses. Von Neumann quickly recognized that his ideas could be applied to the game of business. So in 1944, he teamed up with economist Oscar Morgenstern and wrote Theory of Games and Economic Behavior. The book revolutionized the field of economics. At that time, economists focused on how each individual responds to the market and not how individuals interact with each other. Von Neumann and Morgenstern argued that game theory provides a tool to measure how each player's actions influence their rivals. With the minimax solution, there was at last some mathematical way to help figure out the best strategy in a zero-sum game. But the problem remained, is there a best strategy for a non-zero-sum game like the prisoner's dilemma? The complexities of non-zero-sum games were of great interest to the mathematician John Nash. In a series of articles published between 1950 and 1953, Nash produced some amazing insights into these kinds of situations. While still a student at Princeton, Nash realized that in any finite game, and not just a zero-sum game, there is always a way for players to choose their strategies so that none will wish they had done something else. For the prisoner's dilemma, the best strategy is always to defect. That is a pure D strategy. The minimax theorem had already showed why in terms of costs and benefits, but Nash's insight was about behavior. If I play my strategy against your strategy, is there a point where changing my strategy won't help me? The answer is yes. Knowing that and searching for that point creates what Nash called a strategic equilibrium in the system. And the strategy that creates that equilibrium is now quite naturally called the Nash equilibrium. However, this didn't necessarily mean that the payoffs to each individual are desirable. So it still looked like selfish interest was the rule in game theory. But as we said, people aren't numbers, and they do seem to cooperate, to trust each other, at least sometimes.
You ratted me out.
You ratted me out.
So what you reading?
Book on mathematics.
Got a plan when we get out?
Maybe.
What about that drugstore, you know? The one on Broadway?
Didn't we already do that one?
Seems like it's ripe.
I guess. Third time's the charm.
1, 2, 3. 1, 2, 3. 1, 2, 3.
Rock, paper, scissors is a game played by children, adults, even prison guards all over the world. But while it's just a game, it's also an interesting mathematical object, and it's the next step in our investigation of game theory. I'm here with David Krakauer. David is a research professor at the Santa Fe Institute whose work lies at the interface of evolutionary biology, mathematics, and computer science. So David, rock, paper, scissors, just a game for prison guards?
Well, no, I mean, what makes this game interesting is there's no best pure strategy solution. If you take rock, paper, scissors, well, let's play it. Let's say I play stone, well, you play paper.
Yes.
Well, so paper seems to be better than stone.
Right.
So I'll play paper. Well, now you play scissor.
Right.
Well, scissor seems to be the best of all because it's better than the previous move, which
Right.
is better than the previous move,
Right.
so it must be the best. But now you play scissor and I play stone,
And
I
I've lost,
win.
right.
So you've lost. So there's
Yeah.
this peculiar property of non-transitivity of the payoff.
Yes.
And that leads to a strange solution where there is no best pure strategy.
There's no best thing for me to do absolutely
All
every
the time.
time. Right?
Exactly, unconditionally.
Right.
And so, in this game, it turns out the best thing you can do is just play completely randomly. You play each strategy with a probability of 1/3.
So I have to randomize. So that randomization is an example of a mixed strategy. Is that
Exactly.
right?
Mixed strategy simply refers to the probability of playing any one of the pure strategies. And in this case, the
Right.
pure strategies would be paper, scissors, or rock.
Right.
And the mixed strategy specifies the probability associated with each pure strategy. So a third, and a third.
Right, and if I deviated from that in any way, then you could exploit that
I
in
could
some,
exploit it.
in some
Yeah,
fashion.
if I saw that, Dan, you like particularly playing rock,
Right.
I'd pick up on that cue and I'd just start playing paper.
Right.
And then I'd get, overall, a larger score than you.
Right.
And so we have lots of thoughts in our heads and intuitions about things, and we're not quite sure which is right, what's superfluous, and what's real. And so mathematics can help to amplify the weak intellectual signal. And so a good example is, you know, what are our intuitions about cooperation? When should we be nice? When should we not cooperate? And using mathematics and computational modeling, Axelrod at University of Michigan, a political scientist, in 1978 staged a tournament of computer programs competing in a virtual world over the prisoner's dilemma game.